All right, looks like we have a great crowd rolling in here, so let's get started. Good morning, good afternoon, and to some of you, good evening. A warm welcome once again to our global audience. Thank you for being here with us today for the grand finale of our three-part webinar series on PTP ST 2059. Hopefully you were able to attend our first two sessions last week, in which case, welcome back. But if you missed that, thank you for joining today, and look for some recording links to be sent out to you soon. This session is going to be recorded. We will make it available for you to rewatch along with the first two. And today we are focused on PTP commissioning and troubleshooting. This webinar is presented in partnership with Telstream, Imagine Communications, and Arista. My name is Gina Angelia, and I'm part of the marketing team at Imagine Communications. I'll be working behind the scenes today to help out, along with several other outstanding experts from Arista, Imagine, and Telstream. They're here to help answer and moderate questions, as well as engage with you, our audience. So just before we get started, I do have a few small housekeeping items to go over to help you get the most out of today's broadcast. Now, on a technical note, please be advised if you are currently connected to a VPN service, know that it may impact the quality of today's broadcast. So we do recommend, if possible, to disconnect from the VPN to help get you a better signal. If you're having any audio trouble or concerned about your connection quality in general, a reminder that a list of regional dial-in phone numbers was provided in your registration confirmation email. For those of you who may be new to Zoom webinar, there are two key buttons I would like to draw your attention to in this application. You should be able to move your mouse cursor to the bottom of the presentation window, and you'll find them there. The first is our chat window, where we'll be posting any important messages should the need arise. And if you're having any technical difficulties, you can use that raise your hand button as well, and we will come to you in chat and try and help you out. Now, more importantly and more interesting is the question submission button, that Q&A button at the bottom there. We welcome everyone to add their questions to this box at any time during the live broadcast. If you do have a question about the material presented, it's the Q&A box you're going to want to use so that our experts behind the scenes can see that, and they will be answering live during the presentation through that box as well. Anything that we are not able to get to today, we will of course be collecting those questions and forwarding them to our panelists. Speaking of our panelists today, we have once again our three keynote speakers with us, as well as again our experts behind the scene. We have Mike Wadeson, Application Engineer from Telstream, Robert Welch, Principal Engineer from Arista, and our host for today is Lee Whitcomb, Architect at Imagine Communication and SMPTE Fellow. To everyone on our panelist side of the call, thank you for being with us today. And with that, I'll hand it over to Lee. The show is yours.
Thank you, Gina. So as Gina mentioned, this is the third part in our three-part series, and we'll be covering PTP commissioning and troubleshooting today. Just a quick note on some terms here. During the course of this webinar, we'll be using terms such as master and slave, since this is the language used in the standards today. Please note that when using these terms, we're referring to electronic devices and not a person. Work is being carried out within the standards organizations to change the terminology, and the standards will be updated in the future. There's sort of a lot to cover today, so we'll get going here. And one of the key things for this presentation here is that Arista, Telestream, and Imagine, we've developed a lot of knowledge in this area, and we want to sort of share our knowledge so you can sort of help you succeed in your PTP deployments. I'm going to do a quick review of the first two presentations, just covering some of the key items as they relate to this presentation here. So looking at PTP message types, there are 5 different kinds of messages. So you have announce messages, which are sent from the grandmasters and the masters to be able to establish the synchronization hierarchy. These are used in the BMC algorithm, and they sort of contain some parameters about the master. You have the sync and follow-up, which are sort of the main timing messages. So the sync message basically says the time is now, and it's the now pulse. And then the follow-up message basically says what the time was at that last sync message. So together they basically give you your main time messages. To improve the accuracy in a PTP, you need to compensate for the one-way delay. And so there's delay request and delay response messages. So a media node will send out a delay request message, and then the master will reply, and using that information, the media node can then calculate the one-way delay and improve the accuracy of the time in the system. And then the last kind of messages in the system are management messages. The most sort of or one of the key ones that for our industry here are the SMPTE 2059-2 TLV message. So this message contains information that's used for if you want to derive time codes, so it's information around drop frame information and leap seconds and time zones and that kind of information that you want basically distributed to all your PTP nodes. Looking at the clocks, there are three kinds of clocks. You have ordinary clocks, which are kind of like what you'll find in the media nodes or sort of the end devices. Then there's transparent clocks and boundary clocks, and these are what you'll find in some different kinds of PTP switches. So in a transparent clock, one of the errors of time accuracy in a PTP system is how long does that message live in the switch, and that can be variable. So in a transparent clock, it's going to update some of the fields to basically say, how long did that packet stay in the switch? So then the end devices can compensate for that delay. The other kind of switch you have is a boundary clock switch, which is your sort of the main one you'll see here. And what it has is one of the ports is the acts as a slave port, so it receives time from a grandmaster. And then it basically internally redistributes that time, and then on all its ports, it acts as a master. So then it basically distributes the time to all the devices below it. So it acts as both a receiver of time and a transmitter of time. In our network, we want to have resiliency, so we want to have multiple devices that can become the master. So we're going to use something called the best master clock algorithm, or BMCA. And this is a way that between the different potential masters, one is basically decided this will be the active master for our network. Imagine Telestream and Arista. We have a lot of knowledge in PTP. We're all involved in the development of the standards. We've all participated in various interops and these sort of dirty hands events where we've sort of learned and refined the standard. And we've also been involved with many, many deployments. So we've basically seen what things have gone wrong in the field, what's worked well. And from that, we've basically developed these sort of best practices that are from the three companies. And if you basically follow these best practices, then you should have a very successful PTP implementation. In previous presentation, Robert reviewed the best practices. Since that presentation, we've sort of updated it and added a few, and then I've sort of reorganized them so they're in a slightly different order. So they may look a little different than Robert's, but I mean, basically all three companies have sort of worked together to come up with these best practices. So looking at some very sort of high-level general ones is you want to make sure you start with a very solid network design. You want to, if you have a very poor network design, then the PTP which rides on top of it won't work well. So it's important that you have this solid network design and good PTP foundations. Next thing, after you've done that, you want to do commissioning, and that's what we'll be spending the bulk of this presentation on, so we'll come back to that. Also, you want to have a monitoring solution, so you're basically monitoring the health of your network permanently, and so you can detect when issues are coming. Again, we'll sort of cover that in a bit more detail later. The next group of best practices are related to sort of the PTP network and the architecture and the topology. So our best practice here is that you want to use boundary clocks for all the switches. Reasons for this is if you're using something like a non-PTP or a transparent clock, each of the media nodes can see the traffic from the other nodes, and that can put unnecessary load on the media nodes. So by using boundary clock switches, you're decoupling all of the media nodes there. It makes it easier for debugging. There's some security stuff we'll cover in a little bit. Another important factor is all the grandmasters must be synchronized to the same time. So the reason you need to do this is if you have a failover case and the network switches from one grandmaster to another, if they have a different time, then you'll have a time discontinuity in your network, and that will cause disruption. So it's important that you ensure that all the grandmasters have the same time. So some ways you can do this is they each are locked to GPS, so they all have the same sense of time, or you may have sort of special cables that you're running between the grandmasters to help ensure that they remain synchronized. See if your cursor. So between your different, say if you're running with a 2022-7 system, it's important to have these PTP links between the two sides. This ensures that the entire network converges to the same time. So you never want to have a truly air-gapped system. You have maybe from the essence point of view, you may want to separate those that they stay on each of those two sides. But from a PTP point of view, you want to make sure you have one complete network. Ideally, you want to keep everything to PTP v2 or 2.1 that's coming, and not have any v1 devices in your network. This simplifies the design, the testing, and the troubleshooting by having it all one thing. Now, it is possible with some of these best practices that depending on your application, you may need to deviate them depending on your requirements. So you may, for instance, have some very old Dante devices that only support PTP v1, and so you may have to do that. But if possible, you want to do everything in v2. If you have a distributed network, so you have a production mobile with somewhere far away, we recommend that you have one sort of grandmaster and sort of an active grandmaster at each location. So if you lock them both to GPS, then they're both still synchronized, so your grandmasters are still having the same sense of time, but it's sort of going over a WAN can be sort of challenging. In terms of the PTP parameters, you want to follow the values which are in the 2059-2, the 2020 version, which is just about to be published. We'll cover that more in a moment. For your PTP domain, recommend that you don't use either 0 or 127, which are sort of the default values. As we sort of covered in the last session, the reason you want to do that is PTP can seem to work, but isn't working if not properly configured. And if you take a device which is set to the defaults, it'll tend to work, but not properly. So by picking a non-sort of default domain, it'll fail hard and not work at all, and that will remind you, oh, I forgot to configure this device. When it comes to the P1 and P2 values, you want to make sure that all the devices at the same level in the hierarchy. So I mean, a key thing in a PTP network here is that this is an engineered network. You've designed where are my grandmasters, where are my switches, where are my media nodes. It's not just sort of ad hoc put together. There's a very structure to it. So at the highest level, you've got your grandmaster. So in this example here, you've got both of them with the same P1 value. And then what you want to have is a different P2 value. The difference by having a different P2 value, then if everything else is equal, then you can control which device would be the active grandmaster. So that way you just sort of know that. But by doing this, if you have, say, a GPS antenna failure, then it will sort of gracefully fail over to the other device. As you move down in the hierarchy, we go to the switches. So again, at the same level here, we want to have the same P1 value, but we want that value to be a larger numeric value or a lower priority. So this will only come into effect if both of grandmasters fail. So under normal operations, these two grandmasters would decide between them who would be the active grandmaster. If both of them failed, then the switches would take over. And again, you want to have the different P2 values to sort of differentiate so you can sort of manually enforce which one will be the active one. An important one for security is there's this, is that you want to basically not have the issue where you have, say, a rogue master connected to a port and will try to take over your whole network. So the one way a very good way to mitigate that is by using this role master feature in most of the switches. And so what you're going to do there is in your network that you've engineered, you know that my grandmasters can only be this device and this device. And so what you'll do is you'll set all the other ports into what's called a master only mode, in which case the switch will never accept having a master on these ports. These ports are master only. They will never go into a slave state. Now, because in the case that this grandmaster failed, I would then lock to this switch and then up to this SVG here. So we want to make sure that these interfaces that are all sort of valid paths that a legitimate master can be on, we want to set those into both the master slave mode. So this is a very powerful way in sort of securing your network. And then the last one here in the configuration is you want to turn on the SMPTE 20-2 TLV management messages. Even if you're not using this today, it's important to turn those on so that in the future you can add a device that, say, does time code or uses those messages very easily. We've seen through some of the interops and sort of field deployments that there has been some issues with some implementations around management messages. And so our recommendation is that it's better during your commissioning phase to work out some of the issues you may have in your devices or your topology, fix that during the commissioning, and then in the future, it's very easy to turn it on. If you do it the other way around, you may want to add one device or time code, you turn on the TLVs and you may uncover issues in your network, and at that point you're already live and causing disruption. So better to during commissioning, do it up front, and then it's very easy to, in the future, add a device that may need that. I'm just jumping back at the default values. So there were some differences in the defaults between SMPTE and AES, and so they created a committee. We came up with a document, AES-R16, which basically comes up with a new set of recommendations. This is actually being rolled into the SMPTE 2059-2 standard, and so that will be available soon. But basically the key values here are announced interval of 0, a timeout of 3, a sync interval of -3 or 8 messages per second, and a delay request interval of -3 or 8 messages per second. A lot of thought has gone in by various experts to come up with these values. They've been tested at all the various interop and dirty hands, the JTM tested program. It's been very deployed in the field. So unless you have a really, really, really good reason, you should sort of stick to these defaults. They do work very well. The last thing on the practices here is from a network switch configuration, you want to have as much as possible, use a layer 3 network. This will sort of reduce flooding, increase stability and scalability. And if you do need to use a layer 2 network, to make sure you follow the best practices around multicast for layer 2. This will help prevent flooding there. So looking at sort of the 3 key components as we're doing our commission that we need to be aware of, we have our grandmasters, our switches, and our media nodes. You'll also notice that in this presentation series, we've had basically Telestream, who's one of the world's leaders in grandmasters, has helped putting this session together. We have Arista, who's one of the leaders in the switch market. And then we have Imagine, who's one of the leaders in the media node market. So we've had basically experts in these 3 areas help put together these 3 presentations, and those 3 elements will be sort of important as we get into our commissioning. Just a quick example here of what a large system with using 2022-7 for your essence redundancy, and then with the PTP. The one thing to sort of note that PTP redundancy model is a little different than -7, so that's sort of important one thing to watch out. As we look at the network here, we have our media nodes at the bottom, and so those media nodes will be connecting to the blue or red or amber switches. Those may be going up to this might be a spine leaf. We've got our grandmasters connected to each, the blue side and the red side, and then we have our PTP only links between the 2. So just a very typical example. So I said, if you follow these best practices, you should have a very successful deployment. There are cases based on your application where you may need to deviate from these best practices, depending on your application. When you do that, recommend that you basically get design sign-off from your grandmaster vendors, your switch vendors, and your media node vendors. Because we've seen cases in the field where someone may be using a feature that doesn't exist in a device, or their design will not work. And so we've had cases where people have built up the design, and only during the commissioning phase that they actually figure out that there's just no way this could work. So if you fix it up front, it's a much cheaper and easier. So if you are sort of deviating from these best practices, recommend that. Specifically how you go with doing that, if you're working with the Imagine people, we have application engineers that can help review your design. Mike, at Telestream, who would they reach out to?
So at Telestream, it would be a good idea to contact your local sales engineer. He's going to be able to provide you guidance on the equipment and the application. And so just like at the events we've done at JTM and others, we'll be partnering together with all the other equipment vendors like Arista and yourselves.
Okay. And Robert, who at Arista would they reach out to do these reviews?
Anyone and everyone and often. I'm just kidding. Contact your local account team. If you don't know who that is, then you can ping me on LinkedIn or Robert Welch. And our sales teams are actually phenomenal. If they don't know what the answers are, they'll bring in the experts. And as you can tell, between the trifecta between us 3, we typically talk together almost on a daily basis in case there's something that's not in our domain of expertise, but everybody else. But your primary contact is your SE and your AM that's local in your geography.
Okay, very good. Okay, so you've designed your system, you've built it. Now you need to verify that it's working properly. Now, one thing I mentioned about PTP is that it can appear to work properly when it's not. It may not be meeting your performance guidelines. The failover might not be right. So this is sort of important, that point that it may seem to work, but it's not actually working. And these can arise from, there may be sort of design issues in how you've designed your PTP system. There may be certain devices that are missing features that you were hoping that exist, but maybe an optional feature which wasn't implemented. You may have configuration errors, which can cause this. And unfortunately, some devices have bugs, and so there can be bugs that can cause this to occur. So you want to go through and make sure, is your system truly working? Just some examples here where things seem like they're working but weren't. We've seen cases where like the delay requests by default in many switches are set to 5 or 1 message every 32 seconds. If that's occurring in terms of, say, initial lockup performance is, I mean, a lot of people may want to aim for like 10, 15 seconds for lock performance. Well, if you're only getting 1 message every 32 seconds, you're not going to meet that goal. Now, if you leave the system there running for a while, it will eventually lock up. So it does work. It just doesn't meet your performance goals. We've seen other cases in the field where a grandmaster was varying its message rate from 1 to 3 seconds. And so once it hits 3 seconds, many of the devices in the network were sort of timing out, thinking that the grandmaster had failed. And so there was a lot of BMCA going along and other grandmasters occurring. So the system was kind of working, but was working a little bit weird. Seen other examples where a device stopped sending sync messages and then sent a burst. And so it kind of works, kind of didn't. Other cases where a grandmaster sort of was sending announce messages but no sync messages. And so from a BMCA point of view, it was locked, but it wasn't actually locked because there was no time. Mike, do you have some other examples of what you guys have seen in the field?
Surely. We've had various sort of customer tests where they've gone and evaluated systems and configurations and set up their ad hoc kind of network, either on a tabletop or in a small little rack, to test their devices and the robustness of their cameras and switches and make sure PTP works across their network. We had one customer who had set up such an area within their OB truck facility, all on tabletops and trestles. And then they decided that they wanted to test their 2022-7 redundancy. So they're going to power off the whole particular primary network and switch it off and then see what happens when they brought it back. Well, when they brought it back, it started to have glitches. And so all of the switch signals started to show problems of syncing up to the PTP. So it's then a case of going through and troubleshooting what was going on. And eventually, over the course of a couple of hours, we were able to find out that an orchestration server had made a decision on how it was going to choose which were devices that should be PTP. And that was kind of throwing things off together. So it took a while to find out what was going on, but it certainly was a way to test the system and test the robustness before they actually went on air.
And Robert, do you have some examples of ones you guys have come across?
Yeah, I mean, the domain one is like the common one. Make sure you've got the domains all set right. But of course, you know, there's other situations where people deviate from our best practices we're talking about, and I forget which one it was, which is to stand by and stay steadfast to the 2059-2 specifications. Use those profiles. It's been a lot of work in the background to come up with those. But if you've got the values off on your end node, your media node, and the switch, then things just don't lock. So okay. Yeah, we run across these systems all the time. And the other thing, make sure you get your routing right so you can actually get all the way back to the grandmaster. We've seen that occur too, or maybe they didn't have the rendezvous point right or multicast configured right.
Okay, thanks guys. So in the commissioning process, one thing you need to understand is what is the expected behavior of your network, and then you're going to be basically testing against that. You're going to need to verify those sort of 3 types of devices: the grandmasters, the switches, and the media nodes. Because there's a lot of detail here, you want to have checklists which you've written down and gone through to understand, yes, here's all the things I need to check, because these checklists are quite long. You're going to need various tools to help you run the experiments, to do the test, to do the measurements, and you can check it against that. And then things may fail, and so you'll need to go back and sort of troubleshoot. So we'll sort of cover all these items. So for your checklist, because the behavior and the implications are different on each of those types, you'll have basically different checklists for grandmaster, switches, and media nodes. These checklists are, if you want to do this properly, are quite long. So there is a lot of items to sort of check and verify. And then for each of them, you want to develop a pass-fail criteria. So what is the message rate I expect? What's the tolerance of the lowest bound, highest bound, for instance? So for every item, you need to come up with a pass-fail. So ideally, when you finish the checklist, everything's in the pass category. just looking at the grandmaster checklist, where you're going to sort of be focusing on are things like verifying the master parameter settings in that device. You're going to want to look at what the actual message rates are. So just because you're expecting 1 message per second, is it actually doing that? You want to look at the packets leaving the grandmaster in detail. Also, it's important to verify, is the time in the 2 grandmasters the same? So you want to look at whether they're GPS locked or look at, are they connected to the same reference? So you need to sort of have some steps to verify that. This is just a very small fraction of the checklist, but just to give an example here where you have, say in the grandmaster, you're going to want to make sure, are the priority values set right? The priority 1, the priority 2s. You want to look at the announced messages leaving the device. What's the acceptable range? So even though you set it to 1 message per second, the standard has a certain distribution around that. So you want to make sure it's in this distribution. So I said, this is just a very small fraction of the parameters to check, but just to give you a sample of how you'd want to sort of structure your checklist into various sections based on the parameters, how to measure them, and other parameters. If we look then at the checklist for a switch, now in a switch, say most of them will be in boundary clock, you're effectively acting as almost like a media node at the bottom because you're receiving the timing information, but then on all your other ports, you're acting effectively as a grandmaster on those ports, and so you're basically sending the time down. So the checklist you have for a switch is basically a combination of both the grandmaster's checklist and the media node's checklist. Now, one thing on the switch checklist is that you'll say you want to verify your boundary clock settings. And typically in the switches, there's sort of 2 groups of settings. There's some which are globally applied, so you want to check the globally applied settings, as well as every single interface has certain settings related to that. So you're going to have to check each interface and make sure that they are configured properly, say for instance, like that master-only control. Again, just a very quick sample of the checklist. This again is a very small percentage of what the checklist will look like. But again, you're going through listing all those parameters, what are the acceptable ranges, so when you do your test, you'll check against those. For the media nodes, what you're going to be focusing around is parameters around, is it locking correct? So you'll have checking your parameters, you'll be verifying, is it locking? Is it locking correctly? Because they say, for instance, if you're missing the delay response, delay request messages, your one-way delay calculation would be wrong. You'd still be locked, but your time might be shifted. So you need to sort of get into that low-level detail. And you're basically looking at, for the most part, the devices coming into the media node. Again, sort of part of a checklist. So for instance, some of the parameters you'll want to be checking are, is the device believes it's locked? Is it reporting the right grandmaster ID? That tells you then your network is converged to the right grandmaster and is locking to the correct one. Is the one-way delay within the range that you expect? If it's showing as 0, that may not be working. So again, the actual checklist is significantly longer than this, but it's just a little sample to give you a taste. So how long should you sort of run this test for in this monitoring period? Based on sort of experience, we've seen somewhere between 24 to 48 hours. We've definitely seen there's lots of issues in networks that might occur once every few hours or maybe only once a day. From all our sort of industry experience, within the first 24 to 48 hours, if you have an issue, it'll be in that period there. So if you do a test that's that long, if it's not failing, then you could be pretty confident that your system will work forever. You do also want to be, say, doing a PCAP. You actually want to capture all the PTP packets during this period so you can do a very detailed analysis. Now, fortunately, the PTP rate is very low, so if you set up your capture devices to filter on only the PTP packets, you're looking at 8 sync messages a second, 8 follow-up, and so on. You'll find that even though you're doing like a 24-hour capture, which is pretty long, the files are typically only in the sort of 100 to 200 megabytes in size, and so they're very manageable to use. For the sort of tools to help you with your checklist here, the various devices in your system will have APIs and GUIs that you can get parameters from. So there'll be various status parameters, control parameters. Devices may have counters that you're able to look at. As you get into sort of capturing packets, you'll be able to look at the fields in the packets. You can look at the timing of when the packets occurred, the rates of the packets. You can also scan for unexpected messages, which might indicate there's a problem. When you're doing the captures, you can do sort of port mirroring on the switches, or things like the SPG 8000 allows you to do port mirroring of its port, so you can do it used for capturing. Also, devices like the Prism have capture capabilities so that you can use those to capture the PTP packets. There are various free tools like PTP TrackHound, which allow you to sort of look at the protocol. And many of the devices that you may purchase for doing 2110 analysis of the essence streams often have PTP analysis tools built in. So like the free EBU list tool, or again, things like the Prism have this capability. So looking at sort of a Wireshark capture, so Wireshark is a tool that allows you to look at a packet, and then it runs through a dissection process where it actually breaks out all the fields for you. So by looking at this cursor, so here I've selected a sync message, which is one of the message types. I can look down here, I can see the sync period is -3, and so that tells me that that's set correctly. So by looking at the packet in more detail, I can see that yes, the message believes it's being sent at 8 messages per second, or that -3. Now, important thing is to sort of look at how, I need to check to see, is the actual message rate what I programmed? Because they said we've definitely seen cases where this is not the case in some vendors' products. So to be able to do the port capture, so you need to be able to capture the packets. So a feature that's available in many switches is something called port mirroring, where you can take the traffic from one port and redirect it or make a copy of it on another port, and then you can hook up a capture device to that. So it's a very way that you don't have to disrupt your network. You can just do the testing of it. One thing to be cautious of, though, is PTP processing in many switches is handled kind of in a special way. And so the PTP traffic may or may not be able to be mirrored, or maybe only mirrored to certain ports. So make sure that when you're selecting your equipment, make sure you understand for the switch that you have, can it mirror PTP packets? What are the restrictions of it? You can also use things, like I said, like the SPG you can do for port mirroring. One other technique you can use is, say you're using a boundary clock switch, you can say connect to an unused port. Now, while you're not actually measuring the packets going to, say, your device under test, in most cases, the traffic on any of the PTP ports will be similar. So by doing the test, say, on an unused port, while it's not as good as testing the actual port of device under test, it still can give you a lot of values. And say for specifically here where you want to look at message rates in Wireshark, you can sort of click on the packet type of interest, say sync messages or say announce messages, set the mode in Wireshark to time display format, and it's seconds from the previous packet, and sort by time, and then you can see what is the interval. And then, so here's an example of an issue a customer was having where the grandmasters were sort of constantly hopping around. So had them do this capture here of for like 24-hour period of all the messages. I've now sorted only on announced messages. This capture goes on for many, many pages because it was a 24-hour capture. But just looking at the final capture, where we're expecting approximately once per second, we can see that there's a fair number of messages over that 24-hour period were every 2 seconds. And then there was one message which was actually every 3 seconds. And that's sort of a serious problem. So by using Wireshark here, you're able to see that problem. And so doing this analysis, we actually uncovered several things wrong in their network. One, their grandmaster would sometimes have a message once every 3 seconds, which then caused other devices to go think that the master had failed, run their BMCA, and so it's causing a lot of disruptions. Now also, the media node should have been set to slave only, so they should have never ever tried to become a master. That was something we detected. Also, their role master wasn't set to prevent those media nodes from becoming a master. That was another thing which they should have caught if they'd followed the checklist. And even the timeout was set incorrectly on some devices. So that's why even though there was only one message at 3, some devices were tripping at the 2. So a lot of stuff you can use these tools. Mike, what are some other techniques that you've used in analyzing? Because these files are really big, and what else have you used to analyze this data?
Yeah, while the message rate is relatively low, at only 8 messages a second for like the sync, when you're looking into number of seconds, number of minutes, number of hours to our 24-hour or 48-hour test, then the wealth of the data that you actually have becomes very large. And so I've used a combination of Wireshark to look at the messages, a combination of Excel. So one of the features in Wireshark is you can set up various columns. You can list them out to look at those sync messages. You can add the value for the timestamps or the nanoseconds in there as another column. And then once you've got all of that kind of set up, you can export it to Excel. Once you have it in Excel, then I was tasked with looking at how many sync messages were happening every second. So I want to make sure that that value for the timestamp stays the same for every 8 periods. And so I could use Excel to help me sort through that and compress the amount of data I had to look through by saying, if you see this expression at this particular moment, then make sure it's running at the right rate. And if I find that there's a message rate that only happened 4 times a second, it'll show up within the colorization of the spreadsheet. So you can use those kind of combinations of tools. And of course, then you can use the Prism itself that provides you with that information in the IP session that just simply tells you, this is what your current message rates are within the system.
Okay, good. And Robert, what are some of the techniques you guys can use on the switches for these?
Yeah, we covered a few of this on the prior slide or a prior webinar last week. But one of the things to note is when you're doing this analysis on a port by port basis is look at what the end node is doing. Notice the delay request, delay response. We respond to the delay request messages. So if those are 0, then of course the other side is going to be 0. So just something to look at. You might have to turn on PTP. There might be an extra click on there. Or maybe you have to reboot the switch, not reboot the switch, reboot the end node itself to get it kicked in or something of that nature. But the switch itself is an analytics tool. And you can kind of think of it that way as well. So there's a complement of tools like with the Prism that we were talking about and the switch to analyze what's going on.
Okay, and there's some other sort of screens that you have on the Arista switch that give you some additional information.
Yeah, and this was actually brought up in the chat actually, is what's that offset from master and mean path delay? So what you want to do is you want to set some thresholds in here after you've baselined everything to figure out what that offset from master is. And we're coming up with a white paper that actually tells you what this is. But if you see a large swing in there for some reason, then that's a bad thing. But this is definitely a tool that's available on the switches again to alert you in case there's a mean path delay issue.
Good.
So more
and
tools.
then and then on things like say the media nodes like the SMP, there's various sort of status screens here, so we can see what's the grandmaster I'm locked to, what's my delays, what's the time. So the media nodes also have various things. There's also alarm logs on the SMP, as well as some very detailed logs we'll sort of touch on later. If you do want to sort of get a bit more details on the Imagine, you can reach out to your sales team. So there's an email there, and they can give you more detailed training and sort of demos of various Imagine products. So an important part of the redundancy checking or commissioning process is looking at redundancy failover. And so you want to make sure that if a link fails, you sort of design your system so it will fail over, say, to the other grandmaster. But you want to check to make sure that's actually occurring. Now, as part of this, you need to have a sort of a very good understanding of what is the expected behavior of my system during a failover of this link, this switch, and then you'll be able to sort of test against it. And that sort of includes understanding what is the state of the different ports, as well as what is the timing or the timeline of these events here. An important note is that on any sort of PTP failover from one grandmaster to another, I mean, assuming that they have the same sense of time, which is one of the best practices, you should see no impact on the media node. So the grandmaster ID field should change, and that's expected, but there should be no disruption to the operation of the media node. So you shouldn't see any glitches or changes of output timing or any other thing happen. So as part of your redundancy checking, you're going to want to make sure, does the media node have basically no operational impact during these events? In addition to your failovers, you do want to do a test where you power up the entire system. So you want to make sure that if you power everything down, power everything up, then everything sort of stabilizes and behaves kind of as expected. So going through sort of an example here to see on Mike's presentation, he had a little test for us. So I have a little test here for Robert and Mike here. So I want to look at a failure case and understand what is the expected behavior. So in this case here, my GPS antenna fails. So antenna fails. So a couple of questions we want to know is, what are the sequence of events that occur? And from the media node, what does the sort of media node see in terms of the grandmaster ID changes? So Mike, what's going to happen on the SPG after this antenna has failed?
Just because I want to make sure that you're not going to throw a fast one in here. They're all the right domain. They're all set to the right domain first off, right? So just checking. Okay.
Right. So assume you've done all the other tests and everything else is set up correctly, and we just want to look at the failover behavior here. So anyway, so the antenna's failed. What happens next, Mike?
So when the antenna fails, the clock class of GMA will change from clock class 6 to clock class 7, since it should be set up in holdover mode. So that means that even if it's lost, it'll remain at the frequency. But the BMCA within the system will determine that there's a better grandmaster available that still has GPS lock and a clock class of 6. So the backup grandmaster will change from a passive mode to an active mode and start generating the PTP messages, becoming the grandmaster and distributing those to the switches.
Okay. And from a switch point of view, Robert, what's going to sort of happen next?
Yeah, so we're locked on the left-hand side. So we go from clock class 6 to 7 up on the GM itself. So we're still slaving on that particular port until we hear that BMCA finish, the SPGA on 8000A on the right-hand side. That's when we'll click over to the other one. So we're not in a holdover mode, which we'll see in the next one. We're actually just waiting for it. We're still locked to the original until the other one takes over. So all you'll see is pretty much the GMID change, as well as which of the ports is the master or the slave.
Right, okay. Yeah, so if we look at sort of from the media node, what's happening is it's going to see, I mean, assuming say 2022-7, so you got the two interfaces, we'll see on one interface, it changed before the other interface. So the final state will always be the same, but there'll be all these sort of transient states as different as the grandmasters and the switches are going through their various BMCA things. So from a media node point of view, you'll see one grandmaster ID transition on each interface, and so there'll be a total of 2 for the media nodes. Now, given that the time stays the same in all cases, there should be no disruption at the final media node.
That's right.
Okay, so we have another twist on this now. So instead of the antenna fails, let's imagine the grandmaster or the link from the grandmaster fails here. So here the link, well, so let's say the link got disconnected. So what's going to happen next, sort of, Mike?
So when the SPG basically stops sending those messages, then it's going to have to wait a little bit to recognize that the grandmaster has gone away. And once it starts to figure out that there are other grandmasters available, that BMCA will start again. And it should basically happen that the SPG 8000A is still locked to GPS. It has a clock class of 6. It will become the changeover from passive state again to an active state and become the GM for the network.
Okay, Robert, do you have some stuff to add to that?
Yeah, absolutely. So whereas before we had the BMCA that occurred and all that changed was the GMID pretty much, and everything's nice and in sync. In this particular case, because we are waiting for the BMCA to finish, the grandmaster ID is going to be the switch for a period of time until we actually finish that BMCA. And you'll hear this term called holdover mode. And that's that time period for which we actually identify the new grandmaster.
Right. So if you look through the detailed steps there, the sequence of events is slightly different, but the final end state is the same. So the transient states are different, but the final end state will be the same. And in this case here, if we look at the media node, on each of the media nodes interfaces, we're actually going to see 2 grandmaster ID changes, and that's going to occur on both sides. So the media node's actually going to see 4 in total grandmaster ID port changes occur. Now again, because the 2 grandmasters were sharing the same time, there should be no disruption to the system. So even though there are some transits in the middle, the media node should have no operational impact in both these cases. So as you're doing your testing, you need to sort of understand what is the expectation, and you'll see that in these 2 cases, even though it's just a subtle difference of what failed, the transient behavior is quite different. So this is important as you're doing your commissioning to verify, are things operating correctly? Because when you do your test, you may find if things are not configured right, or if there's some bugs in some of the devices, that some of these steps will be done in a different order or wrong, or you may see glitches on your media notes, which you obviously don't want to do. So for monitoring, it's very important to have a permanent monitoring system set up. What this is basically doing is it's monitoring critical parameters in the system, things like what grandmaster ID you're locked to, what is your lock status. And then it allows you to sort of detect changes in the system, which may indicate that your system is starting to fail. I mean, PTP is very resilient, so as things start to fail, it'll continue to work, but you want to be able to detect that. And one thing SMPTE's been working on is to help in this is a recommended practice, which I believe the name will be RP 2059-15, and it focuses on monitoring. And so one issue we've had in the industry is vendor A has a parameter called lock, and vendor B has another parameter called not locked, and so it's kind of the opposite encoding. And vendor C doesn't even have a parameter related to lock at all. And so as you're trying to monitor this, makes it very challenging because every device is so different. And so we're coming up with our sort of standardized parameters. So we'll say all have a parameter called locked, and we'll all encode it in the same way, that 1 means this and 0 means that. And so you can have then monitoring nodes that basically collect more consistent information in a consistent way from all these devices. So you might be using sort of Cloud Vision or other devices. So it allows you to then get a good sense of your entire system. Also note that the new version of 1588, which was just published with version 2.1, it adds some extra capabilities around this monitoring, because this has been identified as a very important part in sort of making sure that your PTP system is kind of working as expected. Just some examples. So I mean, from monitoring, you've got the SBG has various parameters that can do monitoring. The Prism can report stuff and detect stuff. So you mentioned like the Cloud Vision has a way of sucking this data out. In the SMP, for instance, there's various parameters you have access to. So we're all sort of giving lots of good telemetry that can be used. So as you've gone through this checklist, you may find that things aren't working. And so you need to sort of then do a dive and try to debug things. So in terms of ways you can go through the troubleshooting, so because you've gone through the commissioning checklist, you've got now a lot of experience on how to use the tools, knowing what is the expected behavior. By going through those checklists, you've also probably identified this works, this doesn't work, and that sort of helps to narrow your focus on what's not working. A lot of devices too have sort of supplemental logging. So things like the SMP have some very detailed logs. Whenever a loss of PTV event occurs, the last 20 minutes of information is actually logged to an internal file. And so using that, we were able to say detect, like in one case is where a device had stopped sending sync messages for like 10 seconds. Well, we had a lot of detailed information in the SMP that we could then analyze and find that, oh, here's the issue in your switch. It's not with the SMP, it's with your other devices. Other things like Arista and stuff, they also have various logs. So some of the logs are you can access yourself, and some of the logs you may need some assistance from the vendors. You want to have that monitoring system so you can basically help when you're troubleshooting. If you see that all the devices connected to one boundary clock all fail at the same time, then that sort of helps guide you that, oh, maybe I need to look at that boundary clock. If only one device fails, oh, maybe I need to focus my attention around that. So by giving that large amount of telemetry about the system, that can help you sort of narrow down and troubleshoot what's failing. You may need to sort of add some supplemental logging. As I mentioned, sort of like SMP and other stuff have more detailed logs if you need to do some troubleshooting. And you may have to also add some additional packet capture devices to see, oh, why is this particular interface or this particular device acting a bit weird? And so you may need to add additional packet capture devices to your network while you're doing this sort of troubleshooting phase. So in conclusion here, through our experience in the standards and in the real field development, we developed these best practices between Arista, Telestream, and Imagine. So if you follow these best practices, you should have a very successful deployment. It sort of makes it very easy. One thing to watch out for is that PTP can appear to be working when in fact it's not. So there's very sort of subtle areas you need to pay a lot of attention at the detailed levels. You do want to understand how your network and how your PTP system is supposed to behave so that you can test that against what it's actually doing. For this commissioning, you want to have these checklists that cover both the grandmaster switches and media nodes. They need to be very detailed, going through basically all the critical parameters, so that way you can do that test once, and then you can feel very comfortable that your system is behaving as expected. You do need to do this test and very thoroughly check, so it does take a bit of time and effort. But if you do that once, that'll sort of save you having these weird headaches down the road where my system glitches once a week, and why does that occur? You do want to make sure as part of that commissioning process that you perform your redundancy failover and power tests to see that does it, in the event that my grandmaster, my GPS antenna fail, the system behaves as you expect. Also, as we went through those examples, that certain failures like a GPS antenna failure versus a grandmaster failure, the behavior is different. So you do have to be very careful and think through what is the impact as each link in each device fails. You do want that permanent monitoring system so that after your system is working, if something starts to fail for some reason, you have the baseline of what's good, and then you can sort of detect when things are starting to fail, and that helps in that troubleshooting. And basically, I mean, if you design, implement, and commission your system, follow these best practices, PTP works very well, and it can be very trouble-free. If you don't follow these practices, lots of people have had issues. So, okay, I think we've got a few minutes for some questions. Gina and our back-end panelists there, do you have some questions that we want to go over?
We do, Lee. Thank you so much for the detailed rundown today. I really appreciate it. Our team has been busy behind the scenes answering as many questions as possible. We do have a few that we'd like to ask live. So I'm going to start off with a quick question that's come in a few times regarding those PTP checklists. The PTP checklist that you list there, is that something that's standard or something that you need to develop each time? Right.
So it's a bit of both. So I mean, I've developed sort of checklists for around imagined solutions and using certain like Arista and Telestream devices. You do need to sort of make those a checklist that's specific for your installation. So it is work that you need to do. But say, for instance, I mean, if you're working with Imagine on having that in your system, we can probably share some of those checklists with you.
Makes sense. So question from a couple of people in our audience now. Can these protocols run over a wireless network? And if so, what would that include for 5G WAN or mesh Wi-Fi?
Yeah, that's a good question. I'll take that one. So this is intended for more like a 2110 type of environment. PTP is, as we all know, multicast, but boundary clock oriented to actually get that origination and also the scale, and to keep that tight timing. If you do this over wireless, because it is a shared network, it's kind of like the old CSMA CD. You're not necessarily going to get that tight timing. Also consider, even though we have protocols that do work in compressed mode, you may have other interferences going on. So could it potentially, are you going to get a really good solution out of it? No, you'll probably end up spending more time on troubleshooting than just keeping it wired.
Thanks, Robert. What would common symptoms of PTP failover look like or sound like while in production? And are you able to identify them in front of command lines control systems?
Yeah, so if your system's working well and all the devices don't have any bugs in it, during sort of a failover, there should be no operational impact. So in your production, you should basically see no, like your essence flows, your on-air production, what's going to air should have no glitches, no issues. Now, not to say that some devices don't have bugs and that occurs, but if devices are implemented properly, then you should see no impact. You will see, say, in your monitoring system, you'll see that, oh, the GMID changed, and so it'll alert you to that sort of behind the scenes change. But operationally, if you followed all these principles and have selected devices, well implemented devices, you should see no operational impact.
All right. I have a situational question for you now. So it reads this way. We are installing a PTP network and we keep having instability in our network with the grandmaster ID changing between the SPG and the boundary clock. What's happening here?
Sounds like a bad cable. Could be the bad cable on that. Make sure you got your domains right. And also look at as we showed you, what those characteristics of the delay request, delay response are. If it's not syncing right, then maybe there's something else that's going on. Like, for example, you picked the wrong profile on the SPG. There is a special profile. It literally says 2059.2. Make sure that's right. And then lastly, and most importantly, is on the interface itself, put down the right configuration. We have a white paper that shows what that configuration is. Put that configuration in there because maybe it's bouncing back and forth because the values are off on the profile.
Yep, and definitely as part of your debugging there, I mean, those do that. What you can also look at is things like, I mean, for instance, like, yeah, if one device at the timeout was set wrong, and that one device may think that it's failed, but it hasn't. So make sure things like the timeout values are set the same on both links, that the message rates are set. So I mean, if one was set to 2 messages, or set to 1 message per second, and the other device was configured to say, oh, I'm expecting 1 message every 2 seconds or something, or 2 messages a second, that would cause some issues like that. What you can also do is do like a Wireshark capture, and then do a detailed scrub through the Wireshark capture. So by looking at the traffic, you see the same messages that the grandmaster and the switch are seeing, and so you can sort of understand by the messages you're seeing, should the SPG think that it wants to become the grandmaster, or things like the announce messages missing or gaps, and the same for the switch. So a detailed packet capture can be a very powerful tool.
All right. Thank you, Lee. Thank you especially for all of the detailed review today, and Mike and Robert for weighing in as well. And again, special thank you to our busy Q&A team working in the background. We had some great engagement today from our audience, so thank you all for attending. And we hope that you will reach out to us with your additional questions and that you'll get a chance to review the material again. So we have some email addresses for each of our companies on screen. However, one thing to note, it is arista.com, imaginecommunications.com, and telstream.net. So thank you all for being with us today. And of course, if you'd like more information about PTP applications and products, we invite you to reach out to each of our teams for it. We will make sure that these presentations are available for you to rewatch. Lots of great detail here. Thank you so much, Lee, Michael, Robert, for being with us over the last 3 weeks to give us a master class in PTP. It was certainly appreciated and full of lots of great information. So with that, we'll sign off and we'll tell everybody we hope that you have a fantastic day. Take care.
And one minor thing also is, do keep an eye open for additional PTP webinars. We are looking at adding some additional ones to this series.
Yeah, that's a good point. Real quick, I know we're now over time now, is send us feedback if you want to know more, or go into details on more of this, or have additional webinars like this. Please do let us know. Thank you. Thanks, Gina.
Thank you, everyone.